Oh, recording started. Okay. Welcome to worksheet 7, question 2 walkthrough. This is still recorded during the spring break. And now we're going to look at a somehow design-like question where the question title is called Yes Cap, and we're going to be looking at more fundamentals about the capacitor, this time focusing on the parallel and series interaction of capacitors. So let's first review capacitance and how capacitance is calculated by using part A. So here we have a structure for a peculiar capacitor where first of all, the colored rings and the circles are conductor plates, each with an outer radius of 4 cm, and furthermore, the top conductor plate is a ring. So it has an empty section in between the disc, and the inner section that's empty has an inner radius of 3 cm. The permittivity of the material they put between the conductor ring and the plate is 10 farads per meter, and the vertical distance between the ring and the plate is 3 centimeters. Let us remind ourselves that the capacitance of a capacitor, as spoken in the previous part, is equal to C is equal to epsilon A over D. Here, mind that epsilon is the permittivity of material between the conducting plates. So we know that this is equal to 10 farads per meter. Area here, meanwhile, is equal to 4 square pi over 4 square pi minus 3 square pi, or actually 0.04 meters squared times pi minus 0.03 meters squared pi, because this is supposed to be the overlapping area of the conductors. And last but not least, D is equal to 0.03 meters, which is 3 centimeters itself. So in total, the capacitance is equal to 10 times 0.0007 pi over 0.03 meters, and that is going to give us the capacitance of our capacitor. And this is a plug and chug problem, so you can just directly chug this expression into your calculator and you should get an answer. But the solutions file says that it's 0.73 farads for what I would. So we have reviewed the basics of how to calculate a capacitance in part A. Now, CSM has decided to just use the capacitors they picked up from Corey instead, and they're picking up some 1 millifarad capacitors, 1 mF. They're now going to use the knowledge of resistor and try to see if combining capacitor gives another net capacitor that has different capacitance. So in other words, we're going to calculate the equivalent capacitance of 2 capacitors in series. So let's view this problem generally first. If I have capacitors in series, then the circuit of these capacitors in series will look like this. So first of all, the total amount of voltage across these two capacitors is equal to Vc1 plus Vc2. Second of all, the current across these capacitors is going to be the same. And that is because they're in series. So these two properties hold exactly like how resistor properties hold. Now the different thing is here. The IV relationship between a resistor and a capacitance is different. And it's different in terms that I is equal to C dV C dt. This translates to Q is equal to CV by integrating both sides of the equation. But keep in mind that the IV relationship of a capacitor is I is equal to C dV dt. So I'm going to try using this property to figure out how do we calculate the equivalent capacitance of a capacitor. First of all, since IC1 is equal to IC2, well, that's a typo there. I know that C1 dVc1 dt plus C2 is equal to C2 dVc2 dt. So what that means is, well, first of all, once again, that is equal to IC1 and is equal to IC2, which is just equal to one single value, or one single current. I'm going to summarize this as IC. So that is telling us that IC over C1 plus IC over C2 is equal to dVC1 dt over dVC2 dt plus dVC2 dt. And using the additive rule of derivative, this is directly equal to dVC1 plus dVC2 dt. And this is directly equal to dVC dt, where Vc stands for the voltage across the entire combinational capacitor. And that means that we can derive the above relationship into an IV relationship where IC is equal to 1 over C1 plus 1 over C2 times dVc dt. So the equivalent capacitance then is equal to this coefficient, as this equation completely resonates with the form of an IV relationship in capacitor. So then the equivalent capacitance is equal to 1 over C1 plus 1 over C2. Okay, so here's a full view of our computation. And given that the capacitors themselves are 1 mF, I can then conclude that the capacitors in series has a capacitance of 1 over 1 over 1 mF plus 1 over 1 mF. And that is going to be equal to 2 over 1 mF at the denominator and 1 here, so that's equal to 1/2 mF. Okay, if the solution writes this wrong, I'm sorry. Okay, so now that we have figured out how to use series capacitors, we can move on to thinking about parallel capacitors, which is here. So now, chance of CSM is satisfied with your answer, then we continue to use the knowledge of the resistor and try to figure out the equivalent capacitance of the following configuration of capacitor and figure out the potential energy that this configuration of capacitor carries. So let's look at the equivalent capacitance part first. And once again, let's try to derive the equivalent capacitance of parallel capacitors so that it's easier to move on with. So first of all, suppose I have parallel capacitors, which will then show up in this kind of configuration. So let's try to figure out a couple of characteristics about their I and V. So first of all, I know that the current across this entire capacitor is branched into IC1 and IC2, which is the current of the individual capacitor. And furthermore, I know that all the capacitor has the same voltage. This means IC is equal to IC1 plus IC2 is equal to C1 plus C1 dVC1 dt plus C2 dVC2 dt. And since Vc1 is equal to Vc2, this is actually equal to C1 plus C2 dVc dt. Therefore, the equivalent capacitance is equal to C1 plus C2 whenever C1 and C2 are parallel. And once again, this corresponds to the overall IV relationship form of a capacitor, that I is equal to C dV dt. Okay, so we know that the equivalent capacitance of a parallel capacitor is C1 plus C2, which means that we can simplify our circuit above gradually. So at first we have a 1 mF in series with a parallel capacitor, each of 1 mF. So this gets summarized into 2 mF. And a 1 mF and a 2 mF in series has an equivalent capacitor of 1 over 1 mF plus 1 over 2 mF. So that's going to be equal to 2 over 3 mF. Once again, as addressed in part, as addressed in the first question, the energy a capacitor carries is equal to 1 over 2 CV squared. So this is then equal to 1 over half times 1 over 2 times 2 over 3 millifarad times 5V squared. And this will eventually grant us 8.375 millijoules. And thus we have solved this part of the problem. Alright, let's try to move on to the next part of the question, which should be here. So now we are going to look at this slightly more complicated capacitor circuit. So now we have a circuit of capacitor with two voltage sources. Previously we learned a technique called superposition, but we don't know yet if superposition applies onto capacitor. So let's try to solve this problem, or solve for Vx, using a conventional way first, and then test if superposition also works to solve this. So if I'm going to use the normal way, then I'll first need to define a couple of voltages here. So let's say that I redraw my circuit as the following, just to make things a little more general to work with. All right. So what I'm going to do is I will first try to figure out some characteristics about the circuit that I can work along with. So first of all, the charge across capacitors in the series should be equal. So QC1 is equal to QC2. And this means C1 VC1 is equal to C2 VC2. And furthermore, using KVL, I can tell that V1 minus VC1 minus VC2 plus V2 is equal to 0. So VC1 minus VC2, well actually this should be minus here as well. V1 minus V2 is equal to VC1 plus VC2. And once again, my passive sign convention follows. I should have done this first. Okay. So now, given the above properties, what I'm going to do is I'm going to substitute these expressions into each other to try reaching a conclusion. And I'm going to try to involve Vx as well. So, first of all, what I'm going to do is to state that C1 VC1 is equal to C2 VC2, and I'm going to first try to calculate what is VC1 and what is VC2 so I can give it an expression to work with. So in this case, I'm going to say that C1 VC1, so I'm going to first say that CVC1 is equal to V1 minus Vx, and VC2 is equal to Vx minus V2. This means C1 V1 minus Vx is equal to C2 Vx minus V2. And I'm going to try to put different expressions onto different sides of the equation, and I'll get that C1 V1 plus C2 V2 is equal to C1 plus C2 Vx. Therefore, I actually easily calculate that Vx is equal to C1 V1 plus C2 V2 over C1 plus C2. So now it's time to see if superposition works in this case. If I use superposition, then I have to zero out sources independently to see how they contribute to the total node of Vx. So suppose that I apply superposition to the problem. First I'm going to keep V1, and that means that my circuit looks like this. And Vx is here. So I know that once again, Q1 is equal QC1 is equal to QC2 because they're in series, because C1 and C2 are in series. So C1 V1 minus Vx times C2 is equal to C2 Vx minus 0. Therefore, Vx is equal to C1 V1 over C1 plus C2. If I keep V2 instead, I get the opposite of what I have on the left, and Vx is equal to C2 V2 over C1 plus C2. So I sum these voltages together, and I get that superposition applies by telling me that Vx is equal to C2 V2 over C1 plus C2 plus C1 V1 over C1 plus C2. This is at the end equal to C1 V1 plus C2 V2 for C1 plus C2. Which is exactly the same as I got directly when I'm trying to directly compute. So superposition typically works on linear properties, for example, voltage and current, which can be linear in circuits, but superposition doesn't work on nonlinear properties. For example, superposition will definitely not work when we're trying to calculate the power dissipated across a current source, a circuit component. So that's one thing to pay attention to when you're using superposition. But generally, you will not encounter situations in 16A where you have to apply superposition across capacitors. Even if you do, you can probably directly compute the circuit value using what trick we have shown in the first part of solving this question. So now that we have solved part D, let's move on to the last part of the question, part E. Now, CSM replaces the 1 mF capacitor at the right of the above architecture with another custom capacitor that has a variant capacitor. And the capacitor at the right is now a variable capacitance, where D is the distance that a button is pressed into a switch. Now I also have a voltmeter, which is supposed to read a voltage and return it to a computer, such that the computer can read the difference between the voltage that I receive across a specific capacitor. So the question asks how should I build this circuit, as well as how to compute V of x as a function of D, so that my computer chip can read V of x and decide what to do. So what I can do then is I'm going to first look at the right circuit again, and once again review that Vx is equal to C1 V1 plus C2 V2 over C1 plus C2. And now I replace everything that says C2 with the variable function I have here. So Vx is equal to 1 mF times V1 plus 1 mF over 0.1 minus D times V2. And what I have below is just what I write above without multiplying any voltages. You might notice that we can cancel out the mf across the fraction, and that allows us to build an easier way to write the expressions. And as I have simplified my expression into this form, I'm going to simplify it further by multiplying both sides of the fraction with 0.1 minus d. And eventually, I get that my fraction is 0.1 minus d times v1 plus v2 over 0.1 minus d plus 1. And this is just equal to 1.1 minus d. And this is Vx as a function of d. If I want to read the if I want to read Vx, what I have to do to the original circuit is that I first construct the original circuit, which is somehow shaped like a voltage summer. And now I have to read Vx. Vx is here. So what I have to do is then I connect a voltmeter in parallel to Vx, to some circuit or to something connecting Vx and the ground node. So I have a voltmeter here, and I try to establish a connection between the voltmeter and the computer chip. So that voltmeter can send the information to a computer chip, and the computer chip can then do something to activate switches within my machine. So keep in mind that the voltmeter has to connect from the Vx to a ground node where the voltage is 0V, such that the difference the voltmeter measures is Vx minus 0V, which is equal to Vx itself. So we have solved the entirety of question 2 from here.